Okay, question 2, pulley question. Okay, standard Newton's third law with pulleys connected. Okay, first question is work out the acceleration of one or the other, I've forgotten which. Acceleration of Q as it falls, it's irrelevant. The acceleration of Q and P will be the same because the string is inextensible. Okay, so because the acceleration is the same, okay, we need to work out equations of motion for both of them. First of all, I started looking at the 0.4 meters and U is 0 and seeing we work out acceleration from that, but you can't, it's not a SUVAT question yet, it will turn into one. Okay, but part A, we need to work out equations of motion, F equals ma for each particle. So if we look at P, that's got a mass of 0.8 kilograms. Okay, so we've got forces here, 0.8 g, and R, which will also be 0.8 g since it's not sinking into the table or rising up. Okay, and we've got a tension force, and it's accelerating in that direction. There's no friction, it's a smooth table, you haven't done friction yet anyway. So the only force pulling it that way is tension. So if we look at F equals ma, we get the only force, the resultant force going that way is the tension equals the mass 0.8 times the acceleration. Okay, now we look at Q. Okay, it's got a weight of 0.6 g going down, and it's got the tension slowing it down or decreasing the acceleration downwards. Okay, it's accelerating downwards, so the 0.6 g is bigger. So when we look at F equals ma, we get 0.6 g minus t equals mass 0.6 times the acceleration. So we've got simultaneous equations, okay, and we have to work out A. We add the two equations together, then we get 0.6 g equals 1.4a. Okay, so we rearrange A equals 0.6 g over 1.4, which is 4.2 meters per second squared. Okay. Part B says find the time taken for P to hit the pulley. Okay. So first of all, we need to take the time taken during the acceleration phase. Now it's going to accelerate for the time it takes for Q to hit the floor. Once Q's hitting the floor, then there's going to be no tension left in the string. There's nothing pulling it forward. It will just carry on moving at the same speed. Okay. So we've got two parts. We've got a SUVAT part to it, where we have to work out how fast it's going to be going after 0.4 meters and how long that's going to take. Okay, and we've also got a speed equals distance over time part to it with constant speed for the other 1.1 meter. Okay, so let's look at the SUVAT part of it first. Okay, so we know that U equals 0, A equals 4.2, S equals 0.4. Okay, and we need to work out V and we need to work out C. Okay, I'm going to work out V first because you can just use V equals U plus AT. Okay, so V will equal, I can't use V equals U plus AT, I'm lying completely, sorry. Okay, I'm going to work out V using V squared equals U squared plus 2AS. Okay, and if we look at that, then we get V squared equals U squared is 0, so we get 2 times 0.4 times 4.2, which is 3.36, which gives us V equals 1.833 meters per second. Okay, so that's how fast it's going after 0.4 meters. So when it gets to here, it's moving at 1.833 meters per second. It then carries on at that same speed. There's nothing slowing it down, there's nothing causing it to speed up, okay, for the next 1.1 meters. So, how long does it take to get from there to there? Well, we're still in this SUVAT. If I now use V equals U plus AT, 1.833 equals 0 plus 4.2t. So I get T equals, this is where I messed up, okay, 0.436 seconds for that first bit of a movement. Now for the next movement, we can use speed equals distance over time. Okay, so time equals distance over speed. The distance is 1.1 metre and the speed is our 1.833. Speed doesn't change during that 1.1 metre. Okay, and that comes out at 0.600 seconds. Okay, so when we add those together, total T equals 1.036 seconds, so 3SF 1.04 seconds. Okay, I hope that makes sense. Stay safe.